So there's only one more small announcement related to just logistics of the course. On the 31st, which is the coming Monday, that lecture will be taught by Yao Liang again. He will cover Frank Wolf style methods. And I know some people are working on Frank Wolf style projects, so I hope you get to also contribute some information to the lecture and you get some good stuff out of the lecture. And after that, I will hold the lectures. So the tentative schedule of who's holding which lecture is more or less on the web page, but that can change a little bit. So today we'll continue looking where we started last time, this world of proximal and proximal splitting methods, but we will gradually start moving to very simplistic techniques to do this now for at a larger scale. But before that, and throughout the class today, I will mention several open problems. I wanted to mention some of them last time, I just forgot to. And many of the things I'll talk about today are as simple as what I talked about last time. But even for these simple things, there are several open problems hiding in there. And anytime you solve one, you can more or less write a conference or a journal paper around that. So to recap, just to tell you where we were last time, I just talked I talked a lot towards the latter half about this Douglas-Rachford method, which can be written in that very pretty averaged reflections style. And what was R of F? R of F was so-called reflection operator, which is just a friend of the prox operator. This is just notation for now. An interesting thing is, R of F is minus R of F star. It's a very easy observation, but that gives another picture that using the language of duality, these reflection operators are the negative of the reflection operators for the conjugate, which is easy to prove, but it's the consequence is nicer. So the first line is known as Moros decomposition. I'm just writing it in the operator language. Prox of F plus prox of F star is the identity operator. It's a nice way of thinking about, I think Yao Liang might have mentioned to you, it's sort of akin to a linear operator, or in simpler words, a matrix can be partitioned into a sum of whatever its main component is plus the stuff that lives in the orthogonal subspace, orthogonal complement. So just like you can decompose a linear operator into the basis part that spans its rank and added to it the stuff spanned by its orthogonal complement, in the convex world, the conjugate is sort of like the analog of the orthogonal complement. So you have this very well-known result, Moros decomposition. Moros' original paper is on the class webpage. I put it up, I think, during lecture 1 itself, but like I said, it's in French, so if you don't read French, you might not enjoy it so much. Anyhow, so to that, just do this simple operator calculus, which is why we like this language, and rearrange things, and in 2 lines you have somewhat intuition building insight that reflection operators of F and F star are connected this way. By themselves, it doesn't really change the picture, it just maybe adds a little bit of intuition to your overall understanding of how you think about these objects. Now, the interesting thing that happens, even in the Douglas-Rachford world, is that if now instead of 2 functions, you have 3, what happens? So the naive guess, that doesn't work out. However, it's not entirely junk. This averaged operator in there, like a prox operator, this is actually a firmly non-expansive etc. operator. So if you iterate using this non-expansive style operator, the sequence of z's that you generate will converge to something, but it won't converge to something that you want. So it's not that it's a totally junk iteration, but it doesn't solve the problem.
So which problem would it be solving? Like what would be the objective function that this is?
So yeah, that's a good question. I don't know. So this is like a generalized equation. So it can be characterized to some extent what kind of generalized equation it's solving. So you can cook up an objective function corresponding to that. But unfortunately, even though this looks very pretty, it's not doing the job. And you might think, like maybe I misled you into thinking that doing these games with operators is quite easy. Well, you might say, let's just do the brute force what we did last time, write the optimality condition, play the same games, add x so that we get things in terms of I plus subdifferential. This is what we essentially did when we created Douglas-Rachford. What then? Here I'm stuck. I tried several variations. I think many other people have tried several variations, and I invite you to play with the operator notation to see if you can pull out something from that. And unfortunately, to this date, nobody knows how to pull out something nice from this. A slight, but it's not so bad, a slight progress on this, or maybe substantial progress on this, was made by Borwein and Tam in 2013. What they said is, they said, okay, we know that for 2, this Douglas-Rachford seems to be working. So if we have 3, we'll just pick them pairwise and then apply them. And maybe that will be a good thing. And there's an entire paper on that where they show that it's a good thing and it works and it converges to the solution you want. The paper is originally written just for indicator functions. I just wrote it directly here for general convex functions. So some details are missing. So what they say is, okay, let this T of HF be the standard averaged operator for functions f and h. I wrote it with this notation, T of HF, to stress, this is Borwein's notation, but the reason it's written like this is to stress that first you apply h, because z comes on the right? So first you apply h, then you apply f. So that's why it's written T of HF. So you take the cycle, you first apply fg, then gh, and then hf. So you go cyclically. So this is, they call it cyclic Douglas-Rachford. And they show that this works. So this is one version of the idea. And you can imagine, once I said cyclic, there is nothing wholly about 3. You can take 4, 5, n functions. And this cyclic idea, if it works for 3, by induction, you can show that it works for n.
What do you mean by it works? As in like,
so once you iterate, so if you run this iteration, from that you can extract an optimum solution to that minimization problem. Just like in the 2-block case, you ran this, remember for the 2-block case we ran this iteration, and from that we could pull out an optimum solution to that. So the same thing you can do there. So that's what I mean. Whenever I say works, it means it solves the original optimization problem.
and then the reason you call it a partial solution is because...
So the reason I call it a partial solution is, okay, it will become apparent now. So if you just had 2 blocks, f and g, this actually becomes T of fg and T of gf. It doesn't reduce to the standard dr, so it's doing twice the work somehow. So this guy seems to be doing about twice the number of reflections or prox operators than you would ideally want to do. And nobody knows how to do fewer than these and still solve the problem. So this is like a partial solution, because at least they show under pairwise picking of things you can do. You can solve the original problem, but the open part is, which is I think a fairly difficult open problem, okay, but that shouldn't stop you from thinking about it. That I don't want to essentially, at each iteration, I don't want to compute more than 3 prox operators. I have 3 functions, I just want to pay the price of 3 prox operators, that's it. Okay, is it doable? So a similar question in the world of ADMM, I haven't formally talked about ADMM, but maybe you might see some of it on the homework, but it's kind of very familiar method. Even for the ADMM version, the way ADMM methods are usually written, you're trying to minimize fx plus gx, subject to some linear constraints. And previous theory could show formal convergence only for the 2-block case, like fx plus gx. And only I think in 2012 or 2013 did somebody write, it's a very rather messy to read paper, alleged proof for the multi-block case. But for this Douglas-Rachford world, it's still open. So this is the first open problem, but however,
Yeah. In case of ADMM, also the GX has to be an L2, right? Generally. For the case of ADMM, fx plus gx, the gx generally is an L2 norm between the x and c, right?
Not necessarily. So it is. So in the world of ADMM, what you have is usually generically you can write it like that: fx plus gy, ax plus by is c. So this linear. So this is convex function, lower semi-continuous convex functions, such that whatever this problem has a solution. And the way you write the linearized version of that, you make something called an augmented Lagrangian, which takes the two primal variables, throws in a dual variable, and you throw in plus or minus, whichever notation you like. I prefer minus here. This is the ordinary Lagrangian, and ADMM throws in a quadratic term, which some people call the augmented Lagrangian part. It's nicer to sometimes actually think of it as a proximal part.
So that quadratic is x minus y essentially, right?
So that quadratic is, I should actually formally write it. It is this ax plus by minus c. So it's not x minus y. So the version you have seen with x minus y is probably the following, where you try to minimize fx plus gx. Suppose I have just fx plus gx.
And then you x.
Now you add a y and add a constraint x is equal to y. So this is a special case of this thing, right?
Yeah, you are right.
So, but that's the version that is used to then solve fx plus gx.
But then here again the problem is that it's only true for the L2. The augmented constraint is only L2, right?
So that is yet another open problem in the ADMM world. If your augmentation part, the augmented part of the Lagrangian is quadratic, that version is understood. But if you try to augment it using a non-quadratic function, those things people do implement, but nobody has a formal proof whether it works.
That's what you meant.
No. Here the difference is how many functions can you handle? F plus G plus H. Yeah.
From this 2012 paper, the generalized ADMM to more than 2 blocks. I don't know if the same paper as you read, but the paper seems to suggest that when one has more than 2 blocks, the convergence rate gets slower than the 1 over k.
So this is actually a rather broad statement, right? So I could have blocks where every function is strongly convex. I will be able to actually make it converge linearly. If they are just smooth functions, it'll still, I think you can do it in 1 by k, but I'm not sure. There are some other conditions.
Of the proof techniques, we did not read the same paper.
Okay. But the thing is, even though the paper that is there, it's not that the problem is finally fully settled. Okay, it means the devil's in the details. Which assumptions did the author make? If you make nice assumptions, like some people make nice assumptions, like in this ADMM, when they try to analyze it and come up with an accelerated ADMM method, they make assumptions that A and B are of full rank. Means people suddenly introduce those assumptions, and then when they write a paper, they say, oh, this is a very weak assumption. But when you try to use it on your problem, you say, oh, okay, the assumption doesn't hold.
And the question is whether the same situation happens for Douglas-Rachford. Because when we are trying to deal with 3 functions, do this pairwise kind of update, then we only have 3 combinations of the like 3 chooses 2.
Yes.
But if we extend it to more than 3, you argue that it's the same thing, but I don't know whether the argument...
So the rate of convergence might suffer because of the way you're breaking it up, of course.
And would the eventual convergence be
Means it converges to the solution if there is a solution. So the convergence doesn't suffer. The constants in the rate of convergence might suffer. It might even be that the asymptotic 1/k style thing doesn't suffer, but that thing is within a big O, and the dependence of the constants in the big O can change a lot. So, but it's still, like, this is from 2013, so trying to understand even this version of method is ongoing research work. So Borwein has some more papers on that, but it's I find it was quite interesting because I was looking at DR methods last year, and suddenly, and we were wondering what to do. So last time I taught the class, that time I think that by that time Borwein's paper was not there, so I just posed it as an open problem, but now there's a partial progress. But it would be really nice, at least in theory, if somebody could come up with a direct method to solve that. So there is an alternative technique which people have been using when you have 3, 4, n blocks, which is amenable to ADMM and Douglas Rachford, etc. And what's that technique? That's the poor man's parallelism technique. So if you have more than 2 blocks, there is a way to still make it work. That's actually a very clever technique created by Piera. So let's see. So suppose you are optimizing a sum of several functions. And we saw already that directly, or Douglas Rachford, or for that matter ADMM, they do not apply to that. So what do? So very clever technique, I think, a simple technique but yet very clever technique. So let's look at this special problem. We have m components in the sum, so we are minimizing sum of m different convex functions. And let's see what kind of generic way is there. So you might have seen this technique before, but it's good to, I think, look at it in slow motion and appreciate where it comes from. So the idea is actually simple. The original problem, we are minimizing over Rn for now. And we are not losing any generality by minimizing over Rn, because these Fi's are convex functions. You could make one of them be an indicator function if you want to have constraints in there. So let's just say we are minimizing over Rn. Now, what you do is you have sum of m functions. So you introduce m different new variables. So you massively increase the amount of storage, which is maybe a bad thing, but seems to be hard to avoid paying that price. So now, with repeated variables, you have the new domain just becomes a product space of the old domains, m times. So that's why I'm calling it product space. And you have to add a new constraint that all the xi's are equal. So this is a reformulation of the same problem. And this idea is due to Piera from 1976. I've hardly ever seen his name credited, at least in the ML literature, who use this trick very frequently. But he means, to my knowledge, he's the guy who came up with this simple yet very powerful idea. So what's the powerful thing about this idea? So by massively increasing the number of variables, this has now become fully separable. So you now start optimizing over this big meta variable, which I'll write as bold x, subject to the indicator constraint that all its components are equal. So one way of looking at it is, now you have a variable x that lives in the product space, subject to, I just call it a box, it's like a diagonal in that product space. So now what have we done? This beautiful, I call it technique, has taken that m block thing and turned it into a 2 block problem. And as soon as it's 2 block, you can pull out your favorite method for solving 2 block problems, whether it is ADMM, proximal gradient, Douglas Rachford, or whatever you want. The technique is general, it helps any of those methods, right? And suppose you were trying to implement a Douglas Rachford style method or ADMM method, what subroutine do you need to have? You need to be able to compute prox, right? So prox of f, well, because this bold x is just this x1, x through xm, the prox just factorizes out like that. So you can, so that's why this is also called a parallel proximal method, because each of those components can be computed in parallel completely independently of each other. So it's fully parallel. This is poor man's parallelism, but it's embarrassingly parallel. You implement it right away using a parallel for loop, at least on a multi-core machine. But somewhere the price of that parallelism has to be paid, right? And where is that price paid? That price is paid when you try to implement prox operator for the second guy. So the prox operator of the second guy is prox of an indicator function, which is nothing but projection onto the constraint set, and projection onto the diagonal can be solved in closed form. So that just means finding a vector z. These are bold letters, so these are these block vectors. I turned it over finding a single x for all different yi's. That's what it becomes, because z is in that block, so it has to have all components be the same x. And this is an obvious averaging step, the so-called consensus step. And if you're implementing this either parallel distributed, this is a punishment you have to pay, right? This requires so much communication. But the beauty is, without doing too much, suddenly you have essentially given the ability to handle a sum of m functions to any method that can handle a sum of two functions. So this is a very useful idea. The past few years it was popularized by Stephen Boyd as one of the nice things that ADMM can do. But again, this idea applies to, like I said many times now, any method that can handle sum of two functions can benefit from this idea. So the open problem now in retrospect can be stated in the following way. With the product space trick, you can say handle sum of three functions, four functions, etc. But you have to do this you get the parallelism, but you have to do a consensus step. So the open problem that people have been wondering about is, can I somehow still minimize a sum of three functions without resorting to a product space like trick somewhere? And we don't know. But it's very nice exercise in playing with those operator symbols to maybe see if you can come up with a good iteration. Okay, so let me show you after these two, one more way of dealing with sum of two functions. It's actually sum of three functions, but it'll reduce to sum of two functions. I'm showing you that because I have by now used it already in 2 or 3 papers. It works well in some problems. Yeah.
This might be a dumb question, but so for this problem, if I do descent along x1, x2, x3 parallelly, and then do projection onto that.
These methods are not descent methods.
No, yeah, I know this was not. But if I do like descent along x1, x2 in parallel, and then do a projection on the diagonal, how will that compare to this? Doing just this.
Oh, so the part, so maybe I'm not understanding. So you're saying you compute that, and then you project those onto the diagonal?
So you compute x1 through xn by doing
that prox step
of f1x, f2x, because these are separated now.
Okay, so you're doing coordinate descent.
Yes, kind of, yes.
So you're saying let's do block coordinate descent.
Yes.
You can do that also. So exactly what you're saying is, I have now replicated my variable m fold. I made the problem fully decomposed. However, when you but it might not work. So what you're saying is, I now break up the problem over m coordinates. But now over a given coordinate, you are doing unconstrained minimization. The coordinate is not free, right? It has a hyperplane constraint. Yeah, but I'm saying, so that sounds like a hack, right? You do greedy minimization, but project back. It might not work.
Okay, yeah, okay.
It might not work. I'll later actually show you an example of when this greed can break things. But it's good to think of exactly what you're thinking, because ultimately, in some sense, these methods, so your intuition is though in the correct direction. Let me show you why. These methods are very close relatives or friends of coordinate descent, as you can see by the structure. So I'll show you another example of a 2-block problem. So this is actually first function plus second function plus third function, but the first function has a rather special structure. So we can essentially treat this as a sum of 2 functions rather than 3. And I'll show you this example because even recently, few days ago, we used this as a meta algorithm in a paper, and the student who was working on the paper said to me he finds this method very mysterious. Means he's not in the class, but I'll show you that this method, which I also used to find very mysterious until maybe last year, is not so mysterious. So this method is called Proximal Dykstra method. You might have seen it, you might not have seen it. So for those of you who have ever seen Proximal Dykstra method, has anybody seen that Proximal Dykstra method? Okay. So let me then tell you one thing. So everybody who cares about proximal methods should have at least once gone through this paper. Means now there's updated versions of that, but this is a very nice paper written by Patrick Combet and Christophe Pesquet on proximal splitting methods. It has a title in signal processing, but it gives very quick introduction to forward, backward splitting, etc., inclusive of if there are errors in the steps and so on. So it's I recommend this because at least I learned about the world of proximity from this paper when I read it. So anyhow, coming back, so that's the paper where I also saw this proximal Dijkstra method, which is very easy to implement. So what proximal Dijkstra is claiming to do, it takes quadratic plus f plus h and it will minimize that. So if you look at the first problem, that's really nothing but prox operator of f plus h. And we know by now that those operators are not easy to compute, but we want to split them. That's the whole show here. So you run, so it's okay, means if you haven't seen it before, it runs this somewhat mysterious looking iteration. It makes calls to a prox for f and a prox for h and maintains a bunch of other variables which until few years ago used to be called correction variables, because you make a prox step, but then when you update it, you correct it by some amount. So there was like this hand wavy way of looking at it. And this method actually, it's not apparent to see from here that it works to solve that problem. It looks like ADMM, but is not the same, because it has 1, 2, and 3 functions. So the differences crop up in small details when you derive those, but it's closely related. All of these are closely related, but the problem is even a small difference can change the analysis a lot sometimes. So let me remove some of the mystery behind this method, why this works. I just wrote it here in case you have a prox task. You can easily write 1, 2, 3, 4 lines of MATLAB to implement prox operator of f plus h. So it's always a good first attempt. Whenever you have to implement a prox of sums, just write these 4 lines of MATLAB code, and usually it'll be good enough for you. So you can of course do the exercise to, now we are handling only 2 blocks here, but you can also do the product space here to do proximal Dijkstra for 100 blocks. That's not the point. Let's see why this thing works. So let me give you the insight here. So you start with that problem, and now this comes back to a statement that I made long ago, that never forget to look at the dual of a primal problem. So for all the time that I had used this method, this is one of the examples where I forgot to think about the dual, which is why the method remained mysterious. Once you look at the dual, the mystery begins to disappear. Let's see how. So you write the Lagrangian, right? Everyday business for you now. Now let's try to pull out a dual from that. So you do the standard thing. I forgot to put a W in there, whatever. So that's the stationarity condition, right? So far so good. Now you infimize out the stuff depending on Z, stuff depending on W. So you get conjugate of F and conjugate of H. So it's a maximization problem, but I completed the square and I wrote the whole thing like that as a minimization problem. So that's just routine manipulation, but it's very useful manipulation. So now we are trying to look at this particular problem. So let's try to minimize it. And now the ultimate insight here is not as dramatic when you see it, but it is the key thing, that now solve this problem by block coordinate descent. So which is showing that these methods are very intimately related to block coordinate descent, but sometimes you have to go the route of the dual to pull out the coordinate descent part of things. So if you solve this by block coordinate descent, it's not quite done yet. So block coordinate descent would say this, right? Fix mu, get nu, fix mu, and fix nu and get mu. So that's just block coordinate descent, which at least means I haven't yet proved it in class that this block coordinate descent works, but it seems believable because it's at least doing descent. Later we might see a couple of proofs that block coordinate descent works, but for now it's at least more believable that this block coordinate descent thing works. So now to implement the first line, how would you implement the first line? Just differentiate that with respect to nu. What do you get? This inclusion, right? Same for nu, you get a similar inclusion. Now let's try to rearrange these inclusions. We're just messing around with symbols, nothing very special is happening. So let's look at the first guy here. So the first inclusion is just that. I just rearranged this to bring y and mu on the left hand side. So it turns into that inclusion. If it's easier for you, you can just think of it as equality. And that you can rearrange further by writing that nu k plus 1 is just prox of f star to apply to that argument. And the final trick that happens is I once again use this prox of f plus prox of f star is equal to I. I use that in the last line to turn that into just a prox of f. So the reason I'm rewriting it entirely in terms of prox of f, think of it this way: Mr. Lazy Programmer has implemented a single subroutine called prox of f, a black box. You don't want to re-implement it. Your problem is written in terms of f star, but you can rewrite it to just invoke this once implemented, tried and tested subroutine that you don't want to mess with. So we rewrote everything in terms of prox of f, which I think from a software engineering perspective is also a good thing to do whenever you're building any optimization or any sufficiently sophisticated piece of software. Once you have built an optimized subroutine, try to not mess with it. So sometimes you have to reuse that. So that argmin can be written in terms of a prox step. Similarly, the argmin over mu can be written as a prox step. Now throw these together. So these were the inclusions, and these we managed to implement by calls to prox operators. So one final piece of the puzzle. Look back at, sorry, I hate flipping back, but look back at the Lagrangian. There is a Lagrangian stationarity condition which we haven't used so far. So we took the primal problem, turned it into a dual block coordinate descent. We implemented those coordinate descent steps by prox operators, but now we want to pull out primal variables from that. So to pull out primal variables from that, we use Lagrangian stationarity. Okay, So there you use Lagrangian stationarity to rewrite the block coordinate descent using both primal and dual variables. And this was BCD, and once you rewrite it using that condition, out comes Prox Dykstra. Of course, this thing holds in the limit, so there is additional work required to prove that this thing converges, but it shows that this method, which for several years was kind of mysterious, is ultimately just an incarnation of block coordinate descent. So I wrote out this derivation after, I actually didn't realize it, but Francis Bach told me that, it's really just block coordinate descent, you should try it out. And then I went through the math and I saw that indeed it is just block coordinate descent, but somehow this recognition is not so well known.
Is there a reason why Dykstra is there?
Well, this is a different Dykstra, right?
Yeah, the other Dykstra Dij.
That is Dijk, yeah, that's the Dutch spelling. Maybe this is also Dutch spelling. This guy Dykstra has looked at, he's more famous for looking at this particular problem. It's called the projection or nearest point problem. He's most famous for having a method to solve this projection problem. So if you didn't have that constraint there, if you didn't have that the objective function there, and you just wanted a feasible point, that is called convex feasibility problem. It's a very well studied problem, and you could just alternatingly or cyclically project onto the set C1 through Cn, and you would converge to a feasible point. But if you had an objective function, you wanted the nearest point in that set, not just some point, then cycling through and just projecting cyclically does not give you that point. It only gives you a feasible point. Dykstra came up with a method where he says, oh, instead of doing projection, I have to correct it each time. Then I will get the nearest point. And that correction actually is happening ultimately because of these BCD. That correction, what he calls correction, is just essentially dual variables. This problem is a special case of what we wrote here, because X belonging to intersection of convex sets can be just written as a sum of several indicator functions up there. So this type of argument goes through. Anyhow, so Dykstra is famous for that, and all of these things are ultimately, this start from people trying to come up with good methods to solve linear systems of equations. So that was Prox Dykstra. I'll tell you where we used it. So there is something called like total variation proximity operator that people use in image denoising, or some people use it in change point detection and such problems. And a standard way of doing that, so these are some fixed weights. It just penalizes discrete gradients along that dimension and discrete gradients along this dimension. So this is fx, this is gx. These are two different convex functions up there, and we assume that we know how to compute prox for one of those guys. So if you can do that, you can apply some kind of Prox Dykstra method. Interesting thing to note is this is like a prox problem for just one of those functions that itself is subject of, I'm just writing 15, there have been more than 20 to 30 papers just trying to solve that problem. It's kind of oversolved by now, but every few years there's yet another paper on that. I don't know, it's like one of those toy problems that people in optimization, ML, statistics just like to repeatedly keep resolving. I don't know why. Means it's important. The objective function itself is important. So this is the first time I had myself use Prox Dykstra for a non-trivial problem. This had two blocks and we used Prox Dykstra. But I think I should already tell you, in my experience, if you have a sum of several functions, not the two block case, but if you have multiple blocks, f1, f2 up till fm, then the 2-block trick of Prox-Dykstra doesn't apply. Then you need to invoke, at least to our current knowledge, the product space trick. And it seems that the Douglas-Rashford method somehow seems to handle the product space numerically much better than proximal Dijkstra. So similarly, one might expect that maybe ADMM with product space might be better than proximal Dijkstra with product space. You might still cook up a function where some other proximal Dijkstra wins, but roughly from my experience, often the Douglas-Rashford style idea seems to work the best with this parallel product space technique. And understanding rates of convergence, etc., there, characterizing rates of convergence or characterizing rates of convergence in the 2-block case under different assumptions on objective functions, many of these concerns are open problems, okay? So they're easy to implement, but they're somehow not so easy to analyze. You can give maybe for some problems, you can give a 1/k convergence rate rather easily by invoking general theory, whereas the true convergence rate might be linear. So there are big gaps in the understanding of these methods. Okay, so let me go on and talk a little bit about, it's in the same flow, but now we'll take a different approach to minimize the sum of functions. And today I'll mostly talk at a high level about that. Maybe next time maybe in April, beginning of April, I might then tell you some more theory when we cover a little bit of stochastic optimization and so on. So incremental first order methods. So we have looked so far at the separable problems, and there are a bunch of methods, right? So you could directly apply a subgradient method to the whole f, or a proximal forward-backward splitting to that problem, or you can use our newly created product space trick and do some kind of bulky iteration like that, whichever. So what's the main thing here? At each step, you're having to deal with m different subgradients or m different objective functions, right? And here m different variables or m different prox operators. And that is at each iteration, and you have to run many such iterations. Now, often, at least say for machine learning problems, this 1 through m is the number of training data points, which can be then in millions or worse. And these individual FIs are just loss functions of your classification, regression, whatever model evaluated over a single training data point. And doing this bulky iteration means being able to use all the training data points at one shot. And sometimes that's too much to ask for. So people wanted to say, hey, let's try to do lesser amount of work. So instead of then using the entire gradient of f, people ask the question, what if at a kth iteration, you randomly pick some integer between 1 to m? And instead of using the full gradient, just use that partial gradient of that particular term. Now, this looks like a very good engineering hack, right? And in general, a priori, it's not so easy to imagine, I guess, why should this really work, if at all? So engineering wise, it's great because a little bit of progress is doable m times faster, which is very nice, but is it really a meaningful thing to do? So I'll show you a toy example to motivate soon enough that it is actually a reasonably meaningful thing to do. So there is a little bit of history of this method. You might have heard some of these things before. Let me mention here. So this idea of not using the entire gradient, but just using gradient of a component. These things are known as incremental gradient methods. These days they are popularly by many people also called stochastic gradient methods. So they are also stochastic gradient method, but I'll tell you when I talk about stochastic optimization what the theoretical difference between the two is. As far as implementation is concerned, there's no difference, okay? So initially it was most popular as backpropagation or least mean square method, etc. And we have seen the good thing at least in the stochastic style of thinking. If you were just using gradients of some instantaneous component, you don't even need to say pick a random number from 1 through m. You could more or less stream through your data and just process it as it comes along. So that's also good. And some of the intuition why people initially thought that this might work, and in a machine learning setup this is maybe easier for you to imagine. Suppose you have lots of training data. Many of these data points will look quite similar to each other. So your loss functions will actually be rather similar to each other. There's always heavy amount of redundancy, right? So maybe it's okay to then, several different FIs will essentially carry the same amount of information, so you don't need to really add all of those and use all of them. Maybe just using one of them suffices. That's the hand-wavy version. And if we can take advantage of that, you can of course greatly speed up your implementation. And another thing that people have then seen is if you try to use these methods, when you have really started off an optimization, when you're far away from the solution, these seem to work quite well. But when you come closer to a solution, they don't work that great anymore, which is believable, because in some sense, whenever you're close to an optimum, you want higher and higher precision computation. And these methods are not doing that high precision computation because they're not using all the information. So there is no way they can do that, right? But at least in the machine learning world, we don't really care so much about this high precision business anyways. So it's fine for us. But there are several open questions related to the analysis of these types of methods, including looking at them in non-convex setup, even within the convex setup, under different assumptions on the different FIs that make up the total cost function. What can you say about speed of convergence and all sorts of other variations on that. And the bottom line message maybe which is good for this class is that in the analysis of all these scalable methods, randomization is your best friend. It usually simplifies analysis dramatically because you do not have to anymore worry about did I process F2 after F1 or F1 after F2. In expectation, it doesn't really matter at all. And this is really the crux of what randomized analysis gives you for this class of scalable methods. Okay, let me show you a nice example from Dmitry Bertsekas, which gives us some insight why we might expect this stuff to work. Okay, this is a completely toy problem, but I still really like this example. Bertsekas made a very nice example here to give us some more insight why these methods could be reasonable. So suppose we are optimizing over a single scalar x. Everything else that is written there is also a scalar, ai and bi, they are just real numbers. And it has m components. So take the derivative, set it to 0. That's the true answer in closed form, right? Now look at, instead of using the derivative of entire f of x, let's look at just derivative of individual components of the sum. Set a derivative of individual components. If you minimize an individual component, you get the ith coordinate is bi by ai. And now you can look at the interval within which the true x star lies. You can prove that very quickly, that the true x star lies within the min of the greedy xi's and max of the greedy xi's. Means here is the proof, but it's trivial, you can verify that yourself. So, but this is very important, okay, that there is this interval within which the whole gradient solution lies in an interval which we could determine actually using the individual components. Fine. So now if you are suddenly sitting at x, which lies far away from this R, from this interval in which the solution lies, then an individual gradient looks like that. Means that gradient looks like that anyways, but that's what the individual gradient is. This is what the full gradient is. So what's the great thing here now? If you are outside that interval, the partial gradient has exactly the same sign as the full gradient. So far away from the true solution area, the partial gradient also has ability to guide you towards descent. That's the ability the full gradient has, because it has exactly the same sign as the full gradient. This roughly explains when you're far away from the solution, this incremental method is actually a reasonable thing also. And once you're inside the region R, there is no guarantee at all. Once it is inside this interval and in higher dimension box or ellipsoid, whatever you please, the same idea will hold. Inside that, the incremental guy might even have a dynamics of chaos or whatever, right? But outside that, it seems to be useful. And this is what is exploited again and again. So but this is a very nice example, means you should definitely try to remember this nice example. Okay, so I'll now talk about a few other incremental methods, and I'll tell you, maybe let's see if we have some other open problems coming up. So let's look at now, we looked at an incremental method that used gradients, but suppose the m components are non-differentiable, or some of them are non-differentiable, whatever, let's assume all of them are non-differentiable. What now? Well, you could run Rockefeller's proximal point method, which I've struck out because that seems to be super expensive to run, right? You don't want to go do a prox of all the m components. Might not be so easy to do that prox operator here. However, how about instead of doing prox of the entire f, you just do a prox of some randomly picked index. So remember last time I kind of tried to motivate to you that by doing this prox, we are in some sense simulating the behavior of a gradient. And we've already seen successful use of incremental gradient. So it is reasonable to expect that an incremental prox might also work. Well, interestingly, it seems that this method was created by Butsekas maybe just a couple of years ago. Somehow it missed the attention of the community. But it is, I'll show you, it is probably one of the first incremental prox methods that we should have thought about. So the sub-problem is this, and if you have prox operators for the individual components, you can plug and play. So that's a really nice thing about it. So let's see an example. So okay, I wrote this. This is an open problem. I don't know if how detailed or good convergence analysis for this thing is available. If we can understand this better, that's certainly a very interesting paper. At least to me, it's very interesting because you could have non-differentiable f which are still strictly convex or strongly convex. So using prox, can you, despite the non-smoothness, but because you have the power of a prox oracle, can you actually get a linearly convergent method? If not, what is the kind of, what convergence rates can you pull out? Can randomization help you here like it helped the ordinary stochastic incremental method, etc.? So this is a very nice bunch of easy enough to analyze problems, but it's open.
So it might sound like very foolish. So
It's not.
We have rate analysis for prox methods, right?
Yes.
So why can't we use something similar to this?
Means you can, but the thing is the rate analysis is for the entire sum. And what I'm trying to say is that when you have these individual components, connecting that back is not always so easy. But the kinds of techniques that you create for the full prox method, some of those techniques get used as subroutines and lemmas while analyzing these things. But I find this is a really nice thing to analyze. Let me show you why. The reason why, because this idea from 2011 or 2010 helps us solve one of the oldest optimization problems that we happen to still like. So have you seen this problem? Probably you've seen the Fermat-Weber problem. So the Fermat-Weber problem is probably the very first facility location problem. Facility location is has been a popular topic in theoretical CS also. And ultimately some people like to call this problem a geometric median problem, where you're given a bunch of vectors AI which can be called facilities, and these are weights, costs, etc., and you're trying to somehow bring in a new facility which minimizes the cost. So you're trying, that's one way to call it facility location. So this problem is non-differentiable, and people have looked at it since 1700s. That time they were just looking at maybe 3D or 2D, such problems on the plane. And you could solve some of these by compass and ruler if you are good at geometry. But you can look at it actually in general even in infinite dimensional spaces. So we look at only this simplified version today. So assume that norm in there is the Euclidean norm. Assume also that none of the AIs is an optimum. So in 1D, or in whatever 2D, if the points were collinear, then one of the AIs would be an optimum. So that's, but in general, most of the time, none of the AIs will be optimum. So Weisfeld in 1937, he said, let's do the following. If none of the AIs is an optimum, then that thing is actually differentiable. The only time that Euclidean norm is non-differentiable is when its argument is 0, right? If it's not 0, you can differentiate it, and what is its derivative? Its derivative is just x minus ai divided by the norm of x minus ai. So he just differentiated it and did what we have sometimes done, right? The happy-go-lucky style, that you just write down the derivative equal to 0, rearrange terms, and pray that it works. And in this case, you differentiate that, rearrange the terms. So I define an operator t which maps a vector x into that thing, and that thing comes from nothing but taking the derivative of that. The derivative will be something minus something, and you something minus something equal to 0, and once you rearrange it, that's what comes out. That's not so important. I'm just telling you this name because this Weisfeld method is a very well-known method. And assuming that this operator is well defined by saying, I'm assuming too many things, right? For this operator to be well defined, I should never divide by 0 here. So there is no way for me to a priori guarantee that none of the iterates will ever hit AI, but assuming it never does, then this is a reasonable method. So actually Kuhn actually formalized and completed the proof. He did it in 37, he finalized the proof in 73. And this is Kuhn from the KKT conditions. And even now, people now and then write papers about analyzing the convergence of the Weisfeld method, except they try to make it more and more complicated, where instead of Euclidean norm, they try to use LP norm, for which I don't think convergence is yet fully settled, but this is a nice iteration. It converges. And there are hundreds, and just too many papers. But for us, imagine if the number of terms in that summation is very large. Do you really want to run such an expensive iteration each time? So this is an ideal candidate for that proximal, incremental proximal method that I just mentioned. So you just take the Fermat-Weber problem. Now instead of using all, you just pick one of those. Do this argmin, so this is applying the prox of some random component. And in fact, you can do this in closed form. That's a tiny exercise for you. So the part that I don't know is at what rate will this converge. Maybe most likely it's easy to prove sublinearly, but actually, you know, that with the Euclidean norm, that distance function, that objective is strictly convex, and we have a unique solution. And often what happens in many optimization problems is, if you have a unique solution, then there is often a very strong chance of proving linear rate of convergence for things. Those are intimately tied to each other. And we can probably do that here, but it'll take harder work. And sometime in April, I'll show you another instance of exactly this idea, but doing this incremental proximal method in a metric space rather than, which is maybe curved and is not the Euclidean space. But the point being that this idea of doing this incremental proximal thing is actually quite powerful. It goes even beyond ordinary Euclidean space. Okay, so the another close relative is incremental proximal gradients, and here I have just a single regularizer and a bunch of functions. So you can cook up all sorts of variants and create all sorts of methods yourself, you know. I'm just showing you an example of methods that exist, have been used, etc. So you could run a master iteration, but here notice that instead of using x's, I'm using some z's, because what I do is I run an inner loop which cycles through the components individually, and an outer loop which does a prox to combine the answer. You could do that. This is one version, but it seems the version that is slightly easier to analyze is if you're also doing a call to a prox operator always on the inside. But you can clearly see that if m is large, this is going to be much more expensive iteration to implement than the upper one, unless your prox operator is trivial. So this one is quite tough to analyze in terms of characterizing its rate of convergence and so on. But if instead of going cyclically through these indices, you go randomly, then you will get a so-called stochastic incremental gradient method, or there's several variants of that floating around these days. And you can actually analyze rates of convergence under typical assumptions like f is differentiable or f is strongly convex and so on. But the point being, there are these generic schemes, but it really depends on can we really analyze the scheme that we have implemented on our computer. So there's always a gap between what we analyze and what we implement, but we should try to close that gap. So these are just a bunch of examples. Just a high level intuition behind what's kind of common to all of these methods. You can also try to understand the proximal method as a special case of this, okay? High level intuition is, I'm trying to say run a forward backward splitting method here. Instead of using the true gradient, I'm just using an incremental gradient. So one way to view that process is that actually I am using the true gradient, but there is some error in it. And so that means the partial gradient of the ikth component can be viewed as the full gradient plus some error vector. And I'm actually just implementing the full gradient forward backward splitting method or proximal gradient method, but with errors in the gradient. Now, if those errors, say, were to eventually disappear, if they disappear in expectation, then you can get some probabilistic analysis, you'll get some kind of stochastic proximal method which people study. If those errors disappear in the limit, but you don't have any other control over them, you should still be okay, because suppose this method is not working so greatly, but if the errors disappear in the limit, then in the limit this becomes a true method, so it will work. So that clearly tells you that the performance of the method and its analysis depends very critically on, can you understand and control this error? And by error, let's say, what penalty are you paying by not using the full gradient, but by just using this partial gradient? And that is the subject of quite active research. There's been some good progress recently on trying to understand these things. But at a high level, we'll revisit this idea again, that instead of using the true gradient, you use a gradient with error. Is the method still well defined? Well, if the error is well behaved, the method is still well defined. And the reason I'm saying it's good to start thinking in these terms, tomorrow we'll look at, say, a distributed computation which does asynchronous computation. So, well, instead of using the latest available gradient, I use a stale gradient, so I'm using a gradient with error. So roughly speaking, once I manage to analyze one method which has errors, I can try to start branching out to these other specialized kinds of errors and maybe also tackle them. So it's, at a high level, it's good to think of all of these methods being unified by this idea. Okay, so when I say if we can control this error, that's what is subject of active research. People trying to rearrange the computation to decrease the amount of variance that you might have because of too much error.
So like a big assumption that we make is the errors are independent of each other, the consecutive errors, right? Generally that's made in the stochastic.
So okay, you means you have to make some assumption. It's maybe not such a great assumption. So for example, you can also analyze setups where there is always some amount of fixed error that refuses to go away, which is actually what truly happens on a computer, right? Suppose to compute a stochastic gradient, I had to compute eigenvectors, or I had to do some other complicated operation. Well, I'm running an iterative method as a subroutine just to compute the gradient. I'm not going to run the iterative method to completion ever. So I will always have some error. So, but it's a trade-off, how complicated the analysis or what insight you get. So honestly, there is always error.
I mean, I'm just trying to like say that eventually it might be an assumption that all these components are independent of each other, which might be a strong assumption.
So we might look at some methods where it's a reasonable assumption that individual stochastic samples of the gradients are independent of each other. We might also look at where consecutive samples are dependent but weakly dependent. So both versions have been analyzed, of course the latter one being much harder to say something more useful. Anyhow, so convergence, so another important thing is to note here, because of the presence of errors, even a smooth problem behaves more like a non-smooth problem typically. So to usually implement it or to get a handle on it, then the kind of convergence analysis starts depending very crucially on step sizes and so on. But I will talk about actually some explicit methods which manage to make stronger assumptions but then also give stronger conclusions. So just to summarize this world of incremental methods, so today I have talked mostly at a high level, but now kind of you have a reasonable idea, I guess, about the kind of scalable methods and what's the underlying thing to these incremental methods. So near the optimum, these things can slow down. You can actually run an experiment on MATLAB. Suppose you use a fixed step size, which say doesn't go to 0. Run an experiment in MATLAB with that fixed step size. You will see that close to the solution, the objective will start oscillating. This is exactly going back to my scalar example, that once you're in that R interval, cannot really say things very clearly anymore. But you can actually observe that, and no surprise, somebody once even wrote a paper to fully analyze that tail behavior. Means we don't really care about it, but you can observe it very quickly. So diminishing step can lead to convergence, but usually these things, because they're not using full information, have slow convergence, but under some stronger assumptions on how the error arises, or what exact or what precise notion of this erroneous gradient you have, you can get some better convergence rates. So I just wrote the names of kind of currently popular methods which make these different assumptions but then give you slightly stronger conclusion. Yeah.
Another question I have is, in case of this would hold in case of SGD as well, I'm kind of presuming. So, and I think this holds. Then does taking batches, mini batches when you converge to optimum make sense? Does it?
Yeah. So we will look at that. So in the stochastic setting, what we'll try to do is, suppose you're using an erroneous gradient. If instead of using one erroneous gradient, you could batch, say, m of them together, chances are you reduce the variance by a factor of m. And the speed of convergence depends on variance of the noise. So if you can mini batch them and you can exploit that, you reduce the dependence on the variance. So yes, it can help. So that's pretty much it. The open parts again here are, there has been like under nicer assumptions on f, or under different ways of computing erroneous gradients or erroneous subgradients or erroneous proximity operators, right? We only, all of those different versions exist. the analysis doesn't exist yet for all of them. So there's bunch of several open concerns even here. So in summary means at least today I have mentioned to you at least 6 to 7 open concerns. The hardest of the open problems is the Douglas-Rachford version, I think, because many people have tried that for years and years. All the others are actually within easy reach of all of you. Okay, so that's all I'm going to talk today, because I guess yes, there's one more talk, I think, because there's a talk at 4:30. Some of you might want to go there and have a little break before that talk. So I will see